Okay, welcome, Estefani, Erez, Rigni, Lexi, Antonio. Thanks for coming. And the plan today is all about the chain rule. But before we do that, let's jump into the quiz so we can go over how to answer those questions. Okay, so here's the quiz. And it says find the equation of the tangent plane to f of xy equals 5 plus x squared minus 2xy minus y squared at the point 1, negative 2. All right, so we need the equation of the tangent plane. And to do that, what do I have to calculate? A couple things, or a few things. So what needs to be calculated to find the equation of the tangent plane? Yeah, we need to find z at 1, negative 2, and we need to find fx and fy. So first, let's do f of 1 comma negative 2, which is our z. And that we just plug in. We get 5 plus x squared, which is 1 squared, which is 1, minus 2 times xy, 2 times 1 times negative 2 is 4. But it's a minus a negative 4, so plus 4. And then minus y squared is 4, so minus 4. Any questions on that? Okay, and then 5 plus 1 minus plus 4 minus 4 is 6. Then we also need to find the partial derivative of f with respect to x. And there's just a polynomial. This should be pretty simple. The derivative of 5 with respect to x is 0. The derivative of x squared with respect to x is 2x. What's the derivative of minus 2y with respect to x? Yeah, minus 2xy with respect to x is minus 2y. And what's the derivative of negative y squared with respect to x? Is 0. So that's it for f sub x. Okay, but then we need f sub x evaluated at 1, negative 2. And that means we plug in. We plug in 1, we plug in negative 2, plug in 1, you get 2 times 1 is 2. And then minus 2 times negative 2 is plus 4. And that looks like it's equal to 6 again. Then we need f sub y. So derivative of 5 with respect to y is 0. The derivative of x squared with respect to y is also 0. Derivative of minus 2xy with respect to y is minus 2x. And the derivative of minus y squared with respect to y is minus 2y. So now I need to plug in 1, negative 2. So fy of 1 comma negative 2. So I just plug in. If x is 1, we get negative 2 times 1 is negative 2. And if y is negative 2, you get minus 2 times negative 2 is plus 4. And that gives you 2. Any questions on getting these key numbers? Okay, so now we're ready to work this out. So what we can say is that if we want the equation of the plane, the normal vector, this is the way I like to remember it at least, the normal vector is f sub x, which is 6, comma, f sub y, which is 2, comma, negative 1. And then I dot it with the displacement vector, which is x minus 1, comma, y minus -2, or y plus 2, comma, and then z minus 6. And since it's normal vector, that equals 0. Any questions so far? Okay, now I just take the dot product and I'm done. So we get 6x minus 1. And then plus 2 times y plus 2. And then minus 1, I'll just go minus z minus 6 equals 0. Okay, if you want, you could simplify this as, what is it, 6x plus 2y minus z is equal to, and we get minus 6 plus 4 is minus 2 plus 6 is 4. Bring it over, you get -4. Any questions at all on the equation of the tangent plane? Okay. By the way, how do you check your work if you got some extra time? Any suggestions on checking work? Not hearing you all jump in. Yeah, evaluate it at 1, -2, 6. So you plug in 1, -2, 6, and you better get -4. So 6 minus 4 minus 6 is -4, and that works. So again, that's not foolproof, but it helps a little bit. Any questions at all on question number 1? Any questions? Okay, let's go to question 2. And that is, consider f of xy equals x root y. Use the tangent plane at the point 1, 4 to find the linear approximation. Sorry, it should be approximation, not approximate, for f of 0.98, 4.01. All right, so what do I have to do? Yeah, I basically do the same thing that I did before. It's just our purpose is different, but the method is exactly the same. Okay, we first plug in 1, 4. F of 1, 4 is equal to 1 times the square root of 4, which is 2, which is equal to 2. Any questions on that? How about fx? What's fx equal to? That's really easy. Yeah, square root of y, because it's just x times the constant, and that's just the constant, square root of y. And that, by the way, is we need fx of 1, 4. And that is equal to the square root of 4, which is 2. And we need fy. Fy is a little messier, but not too bad. What is the partial derivative of x root y with respect to y? Okay, xy to the -1/2, except it's 1/2 xy to the -1/2. Yeah, not over a half, but times a half. So it's 1/2 times x times y to the -1/2, and fy of 1, 4 is equal to 1/2 times 1 times 4 to the negative 1/2 is a half. And that's equal to a fourth. Any questions so far? Okay. And since I gave you decimals, let's take the 1/4 and make it 0.25. It'll be easier to work with. Okay, so now that we have that, what we're going to do is we're going to say that f of 0.98 comma 4.01 is approximately equal to, and what you do is basically you plug it in the tangent plane equation. Okay, so what we have is fx, which is 2. And then the whole point of the x minus x naught, if you take the 0.98 minus 1, you get negative 0.02. And then plus, and then fy was 0.25. And if you take 4.01, if you take 4.01, I forgot the negative there. There it is. If you take the 4.01 minus our 4, you get 0.01. Any questions on that? And then plus, well, actually, it's technically it's. So then it's plus what? Yeah, plus our 2, because it's f of 1,4. And that's not too bad. 2 times negative 0.02 is negative 0.04. Plus, multiplying by 0.01 moves the decimal twice. 0.0025 plus 2. And notice that negative 0.04 plus 0.0025 is negative 0.375. Plus 2 is going to be 1.9625. Any questions on this idea? Any questions? Okay, so that was the entire quiz. And hopefully it made some sense to y'all. If there's no questions on the quiz, let's move to the next Q&A. Any questions on homework or anything else? But there's your chance. We'll end up taking the tangent plane using the original points and plugging in slightly off points, but land in the same answer. That will work. It's a lot more work though. Yeah, you could do that, but you're literally just doing step and then unstep and step and unstep. And yeah, you'll get back to the right answer, but it's, it's harder. Okay, other questions? Just a note, because I noticed a few of you commented on the homework or emailed me, is that the default is 4 decimal places for what the computer wants. So if it doesn't say how many decimal places, give it 4 decimal places. If it does, then give it the number of decimal places it says. So that's something to note. Some of you are having trouble with rounding issues. And some of that had to do with decimal places, how many places you kept. So that's just a note when you're doing the computer homework. Computers have to, decide how many decimal places to use and then grade on that. So it is important to kind of read that instruction. Oh, here's a mistake. It's May 3rd. Any questions at all on the homework assignment or anything else that came up? Okay, I have a question for you. If there's no questions, I'll ask you a question. Who remembers the chain rule for good old-fashioned functions of one variable? Who remembers how to write out what the chain rule says? Okay, so f of g of x prime equals f prime g of x times g prime of x. Okay, that's correct. Who remembers using Leibniz notation? Because we're going to actually need Leibniz notation. It is not good enough to use Newton's notation with primes, it turns out, because as soon as you move into functions of more than one variable, primes don't work. F prime of xy means nothing. So you definitely don't want to use primes if we're trying to, kind of lead us into functions of two variables. So if you have a function y equals f of x and x equals, say, g of u, then the chain rule, if you're not writing it out, is df over du is equal to df over dx times dx over du. Okay, and what's nice about it is it's kind of works nicely fraction-wise, because the over x and the x on top cancel, and you get df du, and it's beautiful, isn't it? And it's just, all it is a statement about fractions. Do you remember this chain rule? Hopefully you do, because it was a very big part of first quarter or first semester calculus, depending where you had it. But the chain rule is essential in calculus. Okay, now comes the hard part. So the question is, how do we generalize this to functions of more than one variable? Okay, and that's a tougher question, because the problem is, with more than one variable, let's go two variables. You have f of x comma y, and you might have, let's say it's of x and y are both of one variable. X is equal to x of t, and y equals y of t. So let's say we'll run a parameterized curve. The fractions are going to be hard. Can you think of a way to make it work? Because we want df over dt. Any questions on the idea? What's the problem with just kind of looking at the chain rule for functions in one variable and making the fractions cancel, and then you're done? Can you just say, right, equals with a question mark? Is that df over, in fact, I might as well make it in pretty notation. df over dt, is that equal to df over dx? Actually, we can't use d anymore. del f over del x times del x over del t, or dx. If it's one variable, use a d. Are those equal? Do the fractions cancel nicely? Actually, that d is a del. What do you think? Yes, there's a lot of problems with this. One problem is you can't just ignore y. Yeah, maybe x is your favorite letter, but what if someone else's is y? You get a different answer if you do y. Okay, the other problem is over here, when you had a function of one variable, the dx's cancel because you have a dx on the bottom and you have a dx on the top. But here, we don't have a dx on the bottom and a dx on the top. We do have the dx on the top, but what about the bottom? Is that a dx? Yeah, it's not. It's a del x. And del x and dx are different. Okay, it's not just a formality. They're actually different things. So del x means you have a function of more than one variable, and you're just taking the partial with respect to that one and fixing the other one. Dx means that you really only have one variable. So notice if x equals x of t, the derivative really is a dx over dt because it's just one variable. That's a one variable function. X is a function of t. So you can't cancel these. They're not even the same. Any questions on that idea? So what we want to do is we want to deal with both of the issues that you can't cancel and that you can't just ignore y. That can't be right. You can't just ignore y and hope it works. So here's the big theorem. Okay, and this is, so let me write down chain rule for two variable functions. Each of one variable. Put that in red because that's what we're doing. And what it says is let f of xy be a differentiable function and x of t, y of t be a differentiable parametric curve. Okay, so now if you plug in x of t and y of t into f, f becomes a function of one variable, the function of t. And here's the big theorem. It says df over dt, notice it's not del, because f is a function of the single variable t, df over dt equals del f over del x times dx over dt plus del f over del y times dy over dt. Any questions on the big theorem? Okay, and I thought about it for a while when I was writing notes and stuff about should I prove this for you, and I decided nah. It's a pretty evil proof. The book goes into it and it's pages of proof, and I don't know if you're going to get much out of it, but you are welcome to read the book and get the full proof of this. But you're also welcome to just memorize this theorem. Okay, it's not that hard to remember. So it just says if you want to take df over dt, you do kind of what you would expect with the x one. You do what you expect with the y one as a chain rule, and then add them. Any questions on this? All right, so I'm not going to prove the chain rule, but let's verify the chain rule. Actually, it's not but the above chain rule. There's going to be more than one chain rule today for the following example. So let's suppose that f of xy is equal to x cosine of xy, x of t is equal to t squared, and y of t is equal to e to the t. Let's make it e to the 2t just for fun, just so we can use an extra chain rule. Okay, so verify means do it with the chain rule, do it without the chain rule, and show you get the same thing. Any questions on that idea? All right, so let's do it with the chain rule. And what I can do is I can just copy and paste and then substitute as I need to go. We don't want it in red. Okay, what is del f del x? What rules do you need to use to find del f del x? Y is a constant. Yeah, I can use the product and the chain rule. So I'm going to replace del f del x with product and chain rule. The derivative of x is 1. You just get cosine of xy. And then plus x. Guess I need this in parentheses. Plus x times the derivative of the cosine of xy. Derivative of the cosine of xy with respect to x is going to be negative y sine of xy. So stop me if you're not following any piece of this. Okay. And then it's times dx dt. This is easy. What's dx dt? If you can't tell me, you're not paying attention. Or, yeah, so what's dx dt? Good, 2t. Again, that's supposed to be easy. Okay, then plus del f del y. What rule do I have to use for del f del y? Do I need the product rule for del f del y? Yeah, I don't. I just need the chain rule. X is a constant. It's a constant times cosine of a constant times y. And that's just the constant times negative the sine of xy. So del f del y becomes negative. And then it's going to be the constant times the constant, which is x squared, times the sine of xy. And then dy dt. What's dy dt? Yeah, that's going to be chain rule again. Derivative of 2t is 2, and derivative of e is itself, so 2e to the 2t. Any questions on applying the chain rule to find a derivative? All right. What does it mean, verify? Where are the t's coming from? Are they just chosen, or do they relate to the well, they're given in the question. So in the question, x of t is t squared and y of t is e to the 2t. Yeah. So kind of visually, f of xy is a function of x and y. Okay. But now we're going to say we're going to be along this parametrically defined curve, t squared and e to the 2t. And as you move along the curve, by letting t change, how does f change? That's what this does. So that's what this is all about. So what does verify mean? Yeah, we have to do it without using the chain rule. Okay. How do you do it without using the chain rule? So in other words, if I gave this to you as a problem in November of last year, the idea is you could have done this without knowing anything about this quarter's math. And how do you do it? Because we want to find df over dt, and we know how to find df over dt, or we knew how to do that in November, even October. So what's the process without using this chain rule that we just had? Anyone see? Not that tricky. You have to think a little bit, but it's not that tricky. So how do I write f as a function of t? Because all we know how to do, at least if we're verifying, in other words, we don't know how to deal with two variable functions. So I'm going to have this one variable function, f of t. How do I write f as a function of t only? Forget calculus. This is just algebra. Basic algebra. No, it's not basic. It's intermediate algebra. Yeah, we just plug in x of t is t squared and y of t is e to the 2t into x and y. So f of t is x, which is t squared, times the cosine of xy. X is t squared, and y is e to the 2t. Any questions on that? All right, well, now we want to find df over dt. So I'm just going to copy and paste the df dt part because that's what I want. What do I have to use to find df dt? What rules of derivatives? Now we're back to first quarter. Yeah, actually chain double. Chain and double chain and double product. Double chain and double product. So let's start out. Yeah, exactly. One of the reasons why I'm doing this as an example is I want to convince you that the chain rule is a good thing. Because if you don't use a chain rule, it can get really awful. This is pretty awful. It can get much worse. So we take the derivative of t squared, which is 2t, times the cosine of t squared e to the 2t. And then plus t squared. Okay, and then times, now we have to take the derivative, we have to take the chain rule and product rule. So the chain rule says I take the derivative of the inside. Well, we got to take the derivative of t squared e to the 2t using the product rule and the chain rule again. Derivative of t squared is 2t times e to the 2t. Oops, I think I lost. Oh. There we go. So t squared times, where is it? 2t e to the 2t. And then we're going to go plus. And now the derivative of e to the 2t is 2 e to the 2t times t squared, or 2t squared e to the 2t. And then times the derivative of the cosine. Derivative of the cosine is minus. So I'm going to write minus the sine of the inside, t squared e to the 2t. Are those the same? So we did it in two different ways. Did we get the same thing? And the answer is we got some work to do. And the work to do is let's take our first approach. Notice our second approach, you don't have any x's and y's, you only have t's. So let's take our first approach and put the xy's in as t's. So we get the cosine. Did I lose something? No, it's still there. It's just on the next page. There we go. So we get the cosine of xy. And x again is t squared. And y is e to the 2t. And then we have minus xy, that's t squared e to the 2t. Times the sine of xy, which is t squared e to the 2t. Times 2t. And then minus x squared. X squared is t to the 4th. Sine of xy. Xy was t squared e to the 2t. Times 2e to the 2t. Any questions? Any questions on this? Okay, now you kind of have to put it all together and see if you get the same thing or not. Okay, so notice that this first term, 2t cosine t squared e to the 2t. Here's our 2t cosine 2t squared e to the 2t. So that matches. So far, so good. Then, if you kind of break this up, this gives you a 2t cubed e to the 2t times sine t squared e to the 2t with a minus. Well, here's a 2t times t squared, that's 2t cubed, that's good, times e to the 2t times sine t squared e to the 2t. So that matches. And this last one is, and let's make sure I got this right. We get t squared times 2t squared, which is 2t to the fourth, e to the 2t sine t squared e to the 2t. Here we have 2 t to the fourth, e to the 2t, and then sine t squared e to the 2t, so they match. So they're equal. Any questions on the verification process? Okay, this is not a proof, by the way. This is not a proof that the chain rule always works, but at least, you know, we're able to look at one of them. To do it in general is really miserable, actually. And I think you can trust me. Any questions at all on this example? Any questions? Okay, if there's no questions on that, do you think we have every kind of chain rule you'd ever want? Are we done? Yeah, definitely not. Okay. Okay. You want to be done? Yeah, but no, we're not done because this just said we have a function of x and y, and x and y are both functions of a variable t. Okay. Well, the problem is that happens sometimes. More often, you're changing coordinate systems. Okay. So what kind of change of coordinate system have we learned in this class already? With two variables, what's the main change of coordinate systems? Yeah, polar. So usually you don't have an x of t and y of t, you have an x of r theta and y of r theta. And then you want to say, what is the derivative? You given the function of x and y, what's the derivative with respect to r or theta? Does that make sense? So we need a chain rule that doesn't go from two variables to one, but goes from 2 to 2. Any questions on that thinking, the reasoning? So here it is. Okay, and I shouldn't even say here it is. Here they are. Because the problem is you have all these different variables, so we have a derivative for each of them. So here's the big theorem. And let me write chain rule for a function of two variables that are both functions of two variables. What I capped. And here's what it says. Let f of xy be a differential function, and let x of uv comma y of uv also be differentiable functions. Okay, so we're kind of going from the variables xy to the variables uv. Then here it goes. And the nice thing is it's really similar to what we did. Now there won't be any d's because nothing's a function of one variable. There are no functions of one variable for this kind of thing. So del f over del u is del f over del x times del x over del u plus del f over del y times del y over del u. Notice you can't just look at the first one and say, hey, the del's cancel. So del f over del u is equal to del f over del u, and I just need the first term. What's wrong with that? What's wrong with canceling? I mean, it's fractions. Aren't you allowed to cancel a numerator and denominator if they're the same? What's wrong with that, saying it that way? Because that sounds good math, doesn't it? In fact, it looks like the way I've got it written, I'm going to have del f del u is 2 del f del u if I cancel the two fractions and add. Yeah, that's the answer. These are not fractions. Okay, just because we write it to make it look like fractions, partial derivatives are not fractions, period. So that's just something to get used to. Even though they look like fractions, they're not fractions. So you can't cancel, you can't do fraction arithmetic. So instead, here's a formula, period. This is just the way it is. And del f del v, basically do the same thing, but you replace u with v. Del f del x del v, plus del f del y del v. Any questions on this big theorem? Which theorem do you think you use more often? This one or the one we just did? Which do you think is used more often in the real world? Any thoughts? Yeah, this one is used more often in the real world. Which do you think is used more often in just kind of the day-to-day world for ordinary people? Any thoughts? Yeah, so they're equally often because they're both never used for ordinary people. You go to the supermarket, you're probably not going to use the chain rule for functions of two variables for, shopping. Okay, but if you're training to be an engineer, you need this stuff. Yeah, you can get the best deal, but that's not partial derivatives. Okay, but what you do need to do is if you want to be an engineer, or if you want to be kind of in charge of the mathematics of, Rayleigh shopping for corporate headquarters, then you're going to be using this stuff. That's who uses it, not the shopper, but the person who figures out the best strategies. That's who uses it, using hardcore mathematics. So just let you know, we're getting more and more advanced. So if you start talking this stuff to just like friends that are not into math, they're going to hate you. Just a warning. Trust me, I've been there. Okay, so, but these are really important for engineering, for physics, for mathematics, kind of the hardcore STEM. This stuff needs to happen. Okay, so let me give you an example. Okay, and the example is, let f of xy equal xy squared minus 3x find del F over del R. So let's make that a lot bigger. It's way hard to see. Even this one should be a little bigger, I think. All right. Any questions on the question? Okay, so let me tell you where this kind of stuff happens. Let's suppose you have some kind of electromagnetism. So you got an electric field. Okay, so now I'm talking physics. So you have an electric field. So you have some kind of generator of this electric field. And what you found out using some physics is that for this particular electric field, if you want to find out the total amount of electric force, the electric force is equal to xy squared minus 3x. And then the question is, how does the electric force change as you move from the origin? Any questions on the question? And that's what del F del R would be. All right, well, how do we find del F del R? What do we use? In 2 words? Or maybe 3? Okay, we don't need to convert them in. Remember, that's brutal. If you do that and take derivatives, it's much harder. Okay, so let's not do that. We don't need to convert. In a few words, what do we use? Starts with a C, the first word. The chain rule. We use a chain rule. And del F del R is del F del X times del X del R and then plus, I think the easiest is just copy and paste. Del F del Y times del Y del R. Any questions on the idea? Okay, now it's easy, I hope. So how do we get del F del X? How do we get del F del X? Yeah, differentiate with expect to x. Yeah, we take xy squared minus 3x. Think of y as a constant. Take a derivative. You get y squared minus 3. Okay, and again, please stop me if there's anything you don't understand. Okay, well, what you might want to do, might help, is just to remind yourself, let's write down the equations for x and y in terms of r and theta. And x equals r cosine of theta. And y equals r sine of theta. So now I need to multiply this by del x del r. What's del x del r? Yeah, it's cosine of theta. Then I go plus. Now I want del f del y. What's del f del y? A little more than 2x. 2xy. Because derivative of y squared is 2y. X is a constant. So you get 2y times x or 2xy. And then what is del y del r? Pretty similar. Y is equal to r sine theta. Yeah, it's just sine theta. And that's it. We're done. Did that look pretty easy? Okay. Not too bad. Okay, let us take another example. What is kind of with the same example, but we're going to do a second step. So let's call this part A. And then B. Find del squared f over del r del theta. So find the second partial derivative of f that's mixed between r and theta. Well, what do we have to do to find the second partial derivative, del squared f over del r del theta? What do I need to do now for part B? So this is part A over here. So how do I get del squared f over del r to theta? Yeah, I need to take a derivative again, but now with respect to r and theta. So what we need, and what I can do is the following. So we have del squared f over del r del theta is del over del theta of del f del r, which is del over del theta of del f del x del r, del f del y del r added together. Any questions on that? What rule do I have to use to come up with this derivative? To take del over del theta of del f del x del r. Just for this part. What rule do I have to use for that? So what rule of derivatives? Here's a hint. Del f del x times del x del r. That's a hint. Yeah, product rule. Because as a product of two functions, del f del x times del x del r, I need to use a product rule here and here. So that is equal to. So now what we need to do is we need to get these derivatives out of here, figure out these derivatives. We need del over del theta of del f del x times del x del r. So let's write this out. And then plus. Now we're going to have the same idea. But now we're going to take del over del theta of del x del r. So it gets messy. Okay, and then we have to do the same thing with del over del theta of this other guy, of the second term. And what I'm going to do is I could just go plus del over del theta del f del y. So change all the x's to y's. Del y del r, and then del f del y. Del over del theta of del y del r. Any questions on the second order partial derivative using the chain rule? I'm sure you agree it gets messier and messier. Am I right? Okay, I think I'm just going to say it instead of type it. It takes forever to type and I don't want to run out of time. So, which isn't too bad. Del over del theta of del f del x. So to do that, what do I have to use to do del over del theta of del f del x? How do I get del over del theta of del f del x? Okay, I need to use the chain rule because del f over del x is a function of x and y. So del over del theta of del f del x, we use a chain rule with thinking about del f del x as a function of x and y. So to do that, to use that chain rule, then del over del theta of del f del x is going to be del squared f over del x squared plus, and now we're going to have the same idea, times del over del theta, or del x over del theta. And then I have to add doing it to y. So that's going to be del squared f over del x del y. Times del y del theta. And then the rest is just plugging in. What's del squared f over del x squared? Hint is it's very easy. So what's del squared f over del y x squared? Not 2y. So here's our f. Notice this is a linear term in x. This is just x times a constant. Derivative of x times a constant is a constant. The derivative of constant is 0. So this part just goes away and becomes a 0. Isn't that nice? So I'm going to talk it through, but I don't want to do the whole thing because I don't have enough time. So then del squared f over del x del y, that you take the derivative of x and then the derivative of y, and that is going to be 2y. So this guy is a 2y. This del y del theta is, again, y is our sine theta, so del y to theta is sine theta. And then del x del r, x is our cosine theta, so that'll be just cosine theta. And then we've already done del f del x, del over del theta over del x del r. I'll let you do all of this because, again, I'm running out of time and I need to get to a few more things. But you just plug in because I need to get into 2 more things. We have a little time, but not enough to do all the details. The first thing in general is that if you have a function of many variables, f of x1, x2, dot, 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 xn, and it's differentiable, and xi is a function of many variables, u1 through uk, that are all differentiable, then here's the general chain rule. So this is, you could call it the third chain rule, but this actually works for all. It's just hard to read. And that is del f over del ui is del f over del xi times del f over del x1 times del x1 over del ui plus del f over del x2 times del x2 over del u j plus dot 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 plus del f over del xn plus del xn over del xu j. So notice all these are j's. If I said I apologize, but they should be j's. For any j you want to choose, so there's going to be k different chain rules for this. So this does everything at once. If you want to memorize this, you know all the chain rules, but it is messy. Do you agree? Any questions on that? So let me just do a quick example. Let f of x, y, z equal x squared minus 3yz. And x of uv equals 2u, y of uv equals v squared minus u, and z of uv is equal to 4uv. The question is find del f over del v. Okay, any questions on the question? So for the solution, what do we do? We say del f del v equals, and it looks real similar to what we've already done. We're going to say del f del v equals del f del x times del x del v. And then plus del f del y times del y del v. And then plus, same thing with the z's. And that is equal to, what's del f del y? Del f del x, I mean. What's del f del x? 2x. 2x times del x del v. What's del x del v? Nice and easy. What's del f del v? Zero. There's no v, it's a zero, right? And then plus, then del f del y. And del f del y is negative 3z. And then times del y del v, which is two v. Okay, and then plus, then del f del z, which is minus 3y. And then times del z del v, which is for u. Okay, and then you could rewrite this. You could simplify this if you want. The 0 kills that first term. The next becomes 6zv. And then the last one is it's a minus 6zv. And then the last term is minus 12 yu. And that's it. I found del f, del v. Any questions on this idea? Okay, the last thing is implicit differentiation. And I want to give you a warning. The formula for implicit differentiation feels wrong, but it's right. So let me do the simplest example, and that is if f of x comma y equals 0. Okay. Actually, let's go f of x, y, z. Let's do 3 variables. Then what is, we want to find dz, del z over del x. Any questions on the question? Any questions? Now you might think that dz over dx is equal to, or del z over del x would just be, del f over del x divided by del z, del f del z, but that doesn't work. So it is not. Del f over del z, or del x. Over del f over del z. That looks good because the fractions work, doesn't it? Right? If you multiply by the reciprocal, cancel the del f's, you get del z over del x. Isn't that beautiful? What's wrong with it? So what's wrong with saying that? That you can just cancel, you just multiply by the reciprocal and cancel and done? Hopefully you know this by now. Yeah, these aren't fractions. Instead, what we have to do is we need to take the partial derivative of this equation, left and right, in terms of x. And what I can say, if I would take the partial derivative of this with respect to x, then what does that give us? Okay, and then you'll end up with the right answer. And I'm going to skip to the chase because we're almost out of time. And this is the big theorem, is let f of xy be equal to 0, be a differentiable, and define y as a function of x. Then dy over dx equals del f over del x divided by del f over del y times -1. Very important that it's negative. And that has to do with moving things over and shifting. You can trust me on it. Okay. And with 3 variables, if f of x, y, z equals 0, then del z del x equals negative del f del x over del f del z. And del z del y equals negative del f del y over del y del z, del f del z, as long as not allowed to divide by 0. So It's a plug and chug thing, but you got to remember the formula. All right, we're out of time. But if you do an example, all you do is you plug in del f del x, plug in del f del y, and divide. There's nothing tricky about it. You just got to remember that negative sign. So we are out of time, so I'm going to stop.